Okay, good evening. Okay, so we're gonna start. So we're doing areas pretty much. So just like with differentiation, there are two interpretations of integration. And number one is, in either case, it is its motion. So for the derivative, it is about location versus the velocity. Okay, so that's the I find it the simplest way to think about derivative that way. But the second one is, remember, the tangents. The tangents in the tangent lines to curves. So it's like curved geometry. Okay, so that's some of the problems that we looked at, and some of the projects are about how a light would reflect off curved mirrors. Okay, so these are the two interpretations of differentiation. Now we're moving to the next big topic, integration, and once again, two interpretations. Number one is motion, and the same motion except we're going backwards. So that's what you see at the top over there. It is the how you get from. Why doesn't it fit? Happen here. Okay, how to get back from the velocity to the location. So once again, derivative from location to the velocity, and then the integration goes backwards from velocity to the location. Okay, so that's roughly what we do over there. But the second interpretation of the integration is, once again, curved geometry and the areas. Okay, so how it connects, we'll see. But right now, let's just do computational part. The starting point is computational, and so I showed you what Greeks did. The ancient Greeks did the approximation of the area of the circle by regular polygons, and from the inside and outside, and then saw how everything converges. We're not going to do convergence to begin with early on, but we have something that Greeks did not have, and we have computers. So, and we already did that stuff with the velocities, and now let's in tangent lines. The tangent lines are kind of easy. You just, instead of tangent, you look at the secant line. So what's really the challenge? So not a big challenge, but so it's similar here. If we want to approximate the area of the circle, that's the problem. The whole problem right now is how to approximate the area of the circle with nothing but Excel. Okay, so we're going to do it from scratch right now. So let's do it. Okay, so let me. Yeah, thanks. Let me get started. So I'm gonna have. Okay, so first of all, let me refresh your memory about what the circle is. So once again, what the Greeks did not have is the algebra. They not only didn't have computers, they didn't have algebra. So they would not be able to think, would not have been able to think about the circle other than the way they did. So equal distance from a particular center. Okay, same distance. That's their circle. We have a better place. So what we do is we look at the graph of what the circle is, y equals square root of 1 minus x squared. Okay, so that will give me half. Specifically the domain is between -1 and 1. Okay, so that's the starting point. And all we have to do, let's just plot the graph first and then see where it takes us. Okay, so all right. So I'm gonna put here my two. I will put x here. So in this column I'll have x starting with -1. So my -1 will be the initial point. Over here I will also need my h, but it depends on the number of the number of intervals on the x-axis within this interval, within this segment between -1 and 1. Because what we're doing, we are following, I mean, even though the Greeks did not have what we do, what we can follow them, the idea, and the idea is approximation, except we're not going to be approximating with triangles, but rather with rectangles. So then the idea, but then we want to be able to improve better and better, improve our approximation. So I'll start with n equal 10 intervals. So I will approximate my semicircle with 10 bars. Okay, so you'll see it when we plot it. Okay, so then what is my delta x or h step? It is my interval, which has length 2. So it is equal to 2 divided by 10. Okay, so there you go. Each step will be 0.2 as we progress from -1 to 1. So let's do that. So this it's equal to what is it? The previous one plus R2C3. R2C3. That entry 0.2. Okay. So we have progressed from -1 to -0.08. Okay. So down. These are my values, so it go too far, frankly, but that's okay. Well, let me keep it for now. So these are the 10, or rather 11 points between -1 and 1. 11 points, 10 intervals. Okay. Then over here, I will be plotting y's according to the formula. Right? This formula. Okay. So I have to plug in now the formula. That's easy. We've done this before, so I'm writing equal to square root of 1 minus this thing squared. Okay, 0, right? So the point is, the leftmost point is 0, -1, 0. Okay, the rest of them are these. As you can see, this part is problematic because it's outside the domain. The domain is between -1 and 1, so if we step outside, we'll have more. We'll have too much. Okay, let me change this. Okay, so let me plot it. Let me plot it, maybe. Hold on a second. Yeah, like this, and maybe like that. Let me see. So I now I want to have my circle. No, that's not. Doesn't know what it's doing. Here it is. Okay, that's good enough. Okay, so that is my circle. I mean, kind of not very accurate, but out of proportion. But the idea is here. Circle from -1 to 1 goes up to 1, 10 points. Okay. Now, okay. So that's just to confirm that we do have a semicircle. Okay. Now, how do we compute areas? One way to see is let me try to plot. If I change the. No, this one. Okay, here it is. Okay, so this is what I'm talking about. So we first saw the curve, okay, but really the curve is of no interest to us as much as how much stuff lies underneath. Okay, so we have to compute the areas of these bars and add them together. That's the plan. Well, certainly they will be wider, and I wish I could find that location format. Shadow glow, some field border, color, solid line. Can I width it? What? Okay, see what I'm doing? So because they were too narrow and they didn't really reflect of what we're trying to accomplish. Okay, we certainly would like the width of each of these rectangles to be the h.2. So they would fill the interval between -1 and 1. Okay, so I am not going to go all the way, but that's the idea. We have to add these. So okay, so then what we're looking at relative to this picture is this. These are the heights. Okay, so what I put as y is in fact the heights of these rectangles. Okay, so then to find these rectangles, we're going to need what? To find the areas of the rectangles, what do we need to find?
Width times width.
Right, so we need width. Okay, so let's find width here. Okay, so it's uncomplicated. We simply will be subtracting, going along the axis, we will be subtracting the current from the previous one. So it's equal to this minus that. Okay, blue minus red. Okay, and so it's 0.2 naturally. Okay, so, and these are all here. So naturally they're all the same, but hypothetically it is possible to have the same construction with different widths. Okay, so and now I'm going to carry out this plan, but carry out the plan of computing the area. I'm supposed to multiply these and then add it together. Okay, so well that's not too hard. So I'm gonna let's multiply. So it's equal to width times height. Okay, and then these are the ones. Okay. X the number. Okay, so these are the heights. So so areas here. Okay, so it remains just to add them together, and that's uncomplicated. So I'll just put it here, say over here. So area approximately is, I'm going to put the sum of these above, so equal to sum of these. Okay, so what's the meaning of this number?
It's half pi.
It is half pi, right? Half pi. Let's confirm it. So if I put next to it over here, I will simply write pi over 2. Okay, so that's not a bad accuracy. Not a bad accuracy, right? Well, 1.51, so it's still 0.05 difference, but it's not so bad. We're pretty close. Okay, how do we improve it?
You have more intervals.
More intervals, right? So in other words, I'll put here, say, instead of 2, I'll put 20. Okay, the things don't work out because I'm not entirely, because I'm not covering the whole. See, I'm not here all the way through. I have to go all the way through to 1, right? So as you can see, the graph does not give me everything. So okay, so one of them is, we don't need this. Okay, so we're going all the way to 1. Let me correct the picture by extending these. Okay, full circle is here. It's certainly, once again, disproportional, but that's okay. And summation still not correct, because summation is this. So I need to carry out summation for the whole interval, which is this. Okay, you see how the accuracy has improved. It is now 0.02 differential between this and the reality. Okay. So, well, that's the plan. This is the integration as in calculus is based on. It's based on approximation with bars or rectangles, if you prefer, with times length. The meaning of the area then becomes an issue once you realize that there's no way to compute the area of a curved of a curved figure unless it is approximated. Okay, because even though you're told early on that the area of a circle is pi r squared, but that's just the answer. How do you get there? And you do have to figure it out, because once you step away from circles, say maybe I'm talking about some other curves, such as maybe a parabola, then the answer is that Greeks work so hard to find it does not apply anymore. That's the problem. So they did a good job, but it only works with the circle, and then once you have a parabola, you have to start over. Okay. Fortunately, this plan works out no matter what. I could replace the function. This is my function, right? With any function you can imagine, say such as a parabola, hyperbola, whatever, any kind of a trigonometric function, and the plan works out. Okay, so that's the idea. So that we can handle, as far as we can handle these functions, we can handle areas. And the meaning of the area is then, what is the meaning of the area? It is the limit of these. So we know how to approximate like this, and then with that we take the limit of those numbers, and we have the answer which has infinite accuracy. At this point, I think we're doing a pretty good job without limits and without trying to get infinite accuracy. It is an approximation. And it works out pretty well. Just imagine that in real life, I mean, think about it. In real life, you don't have any. There are no perfect circles, right? So whatever you are computing, it is actually quite likely it comes in like in this form, in the form of the data. And so you have a bunch of points, and you need to compute the area. Well, that's all there is, and we know how. That's how. It is when you are trying to develop like maybe laws of physics or something like that, when you make things ideal, and under that idealization that you might actually deal with perfect circles. So you sort of think of the Earth as a perfect circle, the Sun is a perfect circle, and then you want to know what its area is, or cross-sectional area is. Okay, so that's a starting point. Incidentally, I had a similar discussion just this afternoon in my other class, and carried out pretty much the same plan, circle over here. Did pretty much the same thing, but because it's calculus 3, we did not stop there. So just as well, you can see where you're going with this. This is where. You see what happened here?
3D.
It is 3D. Okay, so what's the problem about, do you think?
The volume of the sphere.
The volume of the sphere, right. The volume of the sphere, so the formula is almost the same as what we just saw. The function becomes a function of two variables, and this is the data. This is the heights are of this thing. But beyond that, you do exactly the same thing. You take those vertical bars, multiply the heights by what? By the two widths of the base. Okay, and once again, approximation works out pretty well. These are the numbers. This is the approximation, 2.0807, while more accurate is 4 pi or 6, half of the sphere, is very close to the truth. So as you can see, that idea of approximation of whether it's velocities or areas or whatever goes on throughout calculus.
How do you figure that out? Do you like rotate it about the y-axis?
No, here how it works. Each value, where does it come from? Here it is, a function of two variables. You see the references compared to what we just saw. Our function has only one reference, the x column, right? Well, function of one variable, that's what we're studying. And this we're studying function of two variables, and it has, as I pointed out, each of them has two inputs. The one on the x column, I put x's on the column here, and y on the row. Okay, so and that creates the graph of this function is the sphere, and then you proceed to the next step and compute the volumes. Okay. And then, well, the trickier part is what happens if you go to functions of three variables. What is that?
Like time?
Maybe. No, but then what's the meaning of the volume? That's my question. You certainly can have as many variables as possible, but then if you compute something like that, what is the meaning of the, and all I can say it's like four-dimensional volume. Whatever that is. Anyway, so let's stick to calculus 1 for the time being. So as you can see, the approximation works pretty well, and we just have to, now the next step is limits. From approximations to full accuracy of calculus. So from discrete calculus to continuous calculus through limits. Okay, so let me outline what has happened with this particular problem. So okay, so this is my function xy between -1 and 1. Okay, the graph is a circle. So the idea then is to sample. So sample it. Sample the function, which, as you can see, simply picking a few values on the graph of a function. So strictly speaking, what has happened is this. So I divide it, well, let's keep it simple, maybe 4 on each side, like this, as a starting point. So not 4, but actually it's, yeah, it is 8 intervals. So n is equal to 8 over here. Okay, so these are the values. And then then I have to decide where I'm going to sample them. And I sampled, actually, I think these are the I sampled. So I go, so I skip this one. I need only 1 point per interval, and I could pick the left end of each interval or the right end of each interval. I could even pick the middle point of each interval. But what actually happened is I picked the right one. Well, these are the values. So then when I do this, I throw out the rest of the function. So it is an approximation, so that part is inevitable. Okay, so then these are the only, this is sampling. A sampling of 8 points. So sample points. Sample the function by choosing a few values of x on the interval. Okay, and then now what happens is, remember those bars. Okay, so now I build those bars. I build from these values. These are the heights. So these are the heights f of, well, let me put some specific numbers here. Say what were they? Interval a is equal to -1, b is equal to 1, and then there's a bunch of numbers between them, and they're followed by 1/4 at a time. So it will be -1, -0.75, -0.5, -0.25, 0, 0.25, 0.5, 0.75, and finally 1. So these are these are the endpoints. The endpoints of the intervals. Once again, you have 11 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. We need 8. So as you can see, I did not take the very first one, but just the way I did it this way. Okay, skipping the first one, depending on your preference. It works out either way. And then what I say here are that these are sample points. Okay, so, and they are called usually x1, x2, xn. Okay, so, well, actually, x0, x1, xn are the endpoints, and then the sample points are in between. Let's not worry about that just yet. So I'll have, so my sample points are these, and so I have determined, I found f of, but not by hand, that's the advantage of computers, and then f of -0.5, and so on. Okay, so once again, this is 0.25, -0.25, -0.5, and so and affine, so these are the heights of the rectangles. So now if you want to visualize just the way Excel did, so I will, these are the bases, or these are the bases of the rectangles. They happen to have the same length the way I have chosen, so they're usually they denoted by h or delta x. Doesn't matter, it is the length of the interval divided by the number of intervals, so it is 0.25. Okay, so these are the bases. So, okay, now I'm combining this information, the bases, 0.25, with the heights, in order to compute the areas. But before I do that, let me still plot these. So this is what I do from the just the heights, the sampling. I create I create the bars. So by making clear what my just drawing the rectangles, that's all there is, like this. Okay, so these are the rectangles now. Okay, you can actually see where it's not perfect picture, but you can see the error. The error is, fortunately, there's quite a lot of error actually, but the good news is that they seem to cancel each other. So I am overestimating on left, right? These are the little corners that stick out of the circle. On the other hand, I underestimated on the right. So because those two cancel out, that's why the approximation is pretty good. Okay, but otherwise you can see that pretty a large error. Okay, so these are the bars. So bars, and then let me point it out again. These are the errors. Okay, now let's look at the areas. Areas are in the typical order. We will go with heights times width, and that's what Excel did. So I'll have these will be, so negative 0.75 times 0.25, the first one, then f of negative 0.5 times 0.25, and so on. You don't want to do it by hand. That's the good thing about Excel. So, and then the last one is f of 1 times 0.25 again. So 10 terms, and is the, I'm sorry, 8 terms. 8 terms is the approximation. Of the total area. As the way it is described is of the area under the graph. Okay, the area under the graph. If you would go to the original picture, this is the graph, right? This is the graph, and then this is the area under the graph. Okay, so that's roughly how it works out. These are called the Riemann sums. The Riemann sum of f of x equal to square root of 1 minus x squared, and then there are all the attributes over the interval, negative 1, 1, okay, and what else? N with n equal 8 subintervals. Okay, so altogether this part is called a subdivision. No, it's called a partition. So partition, usually what we mean by partition is you break something into pieces that do not overlap and cover the whole thing. Okay, so they do overlap, but by the intervals that we have, They do overlap, but only by a single point at a time, right? So which is not entirely obvious, and apparently Greeks were, those ancient Greeks were concerned about it. These little overlaps don't matter. So as far as the area is concerned, the whatever lies above this is 0. Okay, so the area will be 0, and so even though it appears twice, right? So these rectangles do have edges in common, but that is the kind of I guess not really hard to believe in, that the area of a rectangle of 0 width will be 0, right? So that's why we're not concerned with it. But this is what we have, this partition, and then that's an approximation. And but then the big deal is then, just like with the derivative, we don't stop here with the difference quotient. Remember, and that's still an approximation. If we want infinite accuracy, we go for the limit. So which means that you have to carry out this little thing as many times as necessary. Not as many times as necessary, but infinitely many times. So do the same for all n. Say it doesn't matter where you start, but you go on to infinity. You never reach infinity, but if you want to take the limit, you got to have infinitely many. You got to have a sequence. So then the let's say Rn, then compute the limit. The limit of the sequence of Riemann sums. So limit Rn with n going to infinity. Okay? If the limit exists, it's called the Riemann integral. Okay, so the integral supposed to represent the area under the graph of the function, but it works in any dimension, including some where that integral might become volume, it may become something entirely unrelated to geometry. So geometry is just an interpretation of what we do. Ultimately, it's all algebraic. Okay, so that's the plan. We have an example. We have a plan of what to do. And so let's now carry this out. Let me see, maybe this part of n going to infinity is a bit hard to show when with Excel, but you probably can imagine. Let me try. Okay, so these are the bars, and then I will increase the number of intervals from 20 to 30. Okay, so and maybe it's not entirely clear, but they become narrow and narrow, and the approximation becomes closer and closer to actual circle. So if I go right now, I went back to and plot the top of these bars, it will be a very nice curve. But I can also go with 100, and well, it's getting better and better because the extension of the interval is not all the way to -1. You don't probably, that doesn't look like there is a way to appreciate the what's happening, but the accuracy certainly improves. So you remember initially we had pretty nasty. Well, actually, if we go back to say 10, the approximation is pretty bad. Okay, so that's supposed to be a circle. It's not. It doesn't look like a circle at all. And then you go to 20, it's already good, and you go on, and you pretty much, I have a simulation somewhere else to show that in a continuous manner, those little things start to disappear. Those yellow corners, they start to narrow down because of the bars becomes narrow and narrow. You can push the top of each of them closer to the actual curve. So on the left they will be going down, shorter and shorter. On the right they will be getting longer, longer and longer, and once again getting closer to this curve like this. And then they fill in. It's like I don't know, like a key maybe. You know, you have a key and with those bars, little bars that follow the shape of the key, and then it opens. Well, so the more you know how the regular lock works, right? So you put in a key with some curvy edge, and then the little rods drop on it, and they have to drop just right in order to open. Okay, so it's something similar, except imagine that instead of like 5 rods, you have 100 at some point. Okay, so now the plan is now to carry out this and actually find, as an example, I'm gonna find the one of the areas from the limit. Where's that thing? Okay, here it is. So I'm going to do something that Greeks were not able to do, I don't believe, or certainly it doesn't seem likely. So what I'm going to do is, once again, as an example, following this plan, I'm going to take the function 1 minus x squared. So 1 minus x squared is an upside down parabola. Okay, and my interest is this. Find the area, and by the area I mean really the absolute accurate area. Just like we know that the area of a circle is with absolute accuracy is pi r squared. So I want a similar situation, but this is a parabola now. So I want to we're going to see that what we're getting is a method rather than just one example, which is hard to work with. Okay, so if we want an absolute accuracy, we want to go with an unspecified number n. So n intervals. Okay, n intervals. So we don't know what n is going to be. We want to compute for every n. We want to compute the Riemann sum and then take the limit. Okay, so whatever the graph looks like now doesn't matter. The point is that I'm going to take my interval between 0 and 1. Okay, so a is 0, b is 1, n is n. Okay, so I split it into n intervals. Well, just as an example, I put 4 points here. As an example like this. Okay, so once again, this is x1, x2, x3, but then it goes on. X naught is usually the left end, xn is the right end. Okay, then I sample. And which one? Okay. So this time I'm going to pick these like this. So rather than going with the right hand, as last time I did, I go with the left hand. Just to show you the difference. So right hand, see the height. Look at the very leftmost point. The height of the bar above this rectangle is determined by the value on the right here. That the value of the function at that point matters. The ones on the left does not. Right? I could just as well erase everything else, and that initial point over here, that doesn't matter. This one does matter. Okay, so and now I'm doing the opposite. It just happens. Okay, so right hand up to xn over here. Xn minus 1, right? So the previous one is xn minus 1, which is included. Now let me erase this. It doesn't seem to fit. So up to xn minus 1, more. Xn minus 1 here somewhere, xn minus 1, then xn, which is 1, 1, and what I'm picking these. Okay, so okay, then we are computing the value of the function. So I'll have f of x1 times delta. Well, let's go compute delta x. Delta x is b minus a over n, which is simply 1/n. Okay, so this is 1/n. 1/n. Okay, and now I'm multiplying. This is what I'm going to do. Summation delta x plus f of x2 delta x, and so on. F of xn minus 1 delta x. That is my Riemann sum. R sub n. Riemann sum. Well, actually, R frequently stands for R, and L frequently stand for the right end with the left end, and now I'm actually doing the left hand, so just as well let me put L here. Ln, left end Riemann sum. Okay, so what are they? F of x1 is am I doing it right? It's not. Oh, okay. So the first one is 0. So no, it is not 0. What am 1 minus x squared upside down. Okay, so it's no, it is. Hold on, why is it? So this is what I'm doing. This is what I'm doing. I'm sampling. This is my sample point, the very first point, and then this is my bar. Okay, first. The first bar has the height delta x. They all do, but the height is determined by the point, the value at x not equals 0, which just happens to be 1. I don't know why I'm missing here. I'm missing the 1. Okay, so okay, let's just continue. So it will be negative 1 over n. No, there's no negative 0. See, 1 times 1 over n. 1 times 1 over n. Okay, okay, plus x2. What's x2? I think I picked the right end, not the. I think I picked the right end. Okay, so we stuck with the left end. Doesn't matter. Okay, so what's the second height?
175.
No. We are doing with n. N is arbitrary, so we are carrying out this plan. So we're done with approximation. Now we wanna have an approximation for each n. So 0.25 would be if n was equal to 4, then we would have 4 points. I drew 4 points, but really I have to write as many as necessary. But well, yeah, I don't want to have a confusion here. So we don't know how many. There are n of them. Okay, so this is 1 over n, 1 over n, 2 over n, 3 over n. Well, that's not a 3 over n, but in fact, so it will be, well, let me write it out. F of 0 times 1 over n plus f of 1 over n times 1 over n plus f of, what is it, 2 over n times 1 over n. And the last one is 1 minus f of 1 minus 1 over n times 1 over n. So 1 over n is repeated because that's the width. The width is the same for all of them. And the heights are still to be computed. Okay, so f of 0, as we know, is 1. f of 1 over n, I'm just substituting them all into the same formula. 1 minus x squared. Okay? So what I'm getting is 1 minus 1 over n squared times 1 over n. Then 1 minus 2 over n squared, 1 over n. And the last one is 1 minus 1 over n squared, 1 over n. Okay? So we simplify. Certainly we factor 1 over n out. That's the easy way. Okay? So we are left with 1 plus 1 minus 1 over n squared plus 1 minus 2 over n squared. And here still 1 minus 1 over n squared. Okay? So so what do we do next? There is a significant simplification here. Look at the ones. One is repeated. How many times? N times. So if I take it out and then divide by n, I will have 1. So it's 1 plus what's left. So it is minus 1 over n. Well, I guess I could factor minus out as well. Why worry about it? So I'll just put a minus here, and I have 1 over n squared plus 2 over n squared, plus that the last one is 1 minus 1 over n squared. 1 over n. Okay, so we are simplifying these things little by little. So I guess we can make one more step. Let me do the let me change this one. It is 1 minus 1 over n is simply n minus 1 over n, right? N minus 1 over n. Okay, that way now I can do common denominators. Let me do common denominators. I have n terms, and I have 1 minus 1 over n. What's the common denominator for all of these? No, n squared, right? N squared. And here I have 1 squared plus 2 squared plus n minus 1 squared. Okay? So we are out of time, but we'll finish it tomorrow. So we actually can take this all the way through and find the absolutely accurate answer to the question. Okay?